The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So if you guys don't remember me, I'm one of your TAs. I'm TA number 3. That's what I call myself. I'm KN, and I'll be teaching your lesson today because, well, Mike's in Russia. So yeah. So I know you guys had your first exam a couple of days ago. How did that go?
Pretty good rush. It's not tough.
Okay, sounds good. All right, so we won't talk about it. But because you guys just had a super kind of intense exam, we just want to give you guys a break. So today I'll be teaching you guys a little bit about nuclear energy. So this lesson won't be super in-depth. There won't be a lot of crazy intense math. Actually, there won't be any crazy intense math because we just want to give you guys a break. You guys are going to be starting up full cycle on Friday with really cool topics like stopping power. So for now, it's just kind of like, it's a refresh over a couple of fun facts. A couple of guys might already know some of the concepts I'm mentioning because you guys are intelligent people, but I walked into MIT not knowing a single thing about nuclear energy, and I was like, I wish someone could have told me these things, so that's what I want to do for you today. Okay? So I'm going to be talking about kind of like the functionality and the benefits and the problems associated with nuclear, but first let's start with a very brief history in a nutshell. So between 1895 to 1945, that's when really cool people were developing nuclear science. So people like Madame Curie or like Fermi, etc. They were all designing this nuclear science. Like they were developing it, which is pretty cool. Most of this development happened between 1939 to 1945. Does anyone want to take a gander as to why? What?
Manhattan Project?
Yeah, exactly. But what field? The Manhattan Project, which is World War II, yeah, exactly. So World War II was happening during those times, and they were trying to develop the atom bomb, which is why the majority of nuclear science was developed between these like 5 or 6 years. Then 1945 to 1960, they entered a phase of like, well, the war's over, now what do we do with ourselves? So luckily they decided to redirect this science into using it for energy and harnessing it in a controlled fashion. So mainly the focus was actually for naval submarines, but they also realized like, we can use this for like energy as well, for electricity as well. So there's a lot of really cool things that happened in between these years. So in 1951, the first nuclear reactor to produce electricity was the experimental breeder reactor, the EBR-1, was developed and designed and operated, and it actually kind of worked. It was created by Argonne National Labs, which is in Idaho, and they actually still exist. So if you want to go work there this summer, you totally can. And then in 1953, President Eisenhower, he created something called Atoms for Peace. So this is just a program that advocated using nuclear for things that were peaceful, such as electricity instead of like nuclear weapons and stuff. Also, 1953 was the creation of Mark I. So Mark I is the first prototype naval reactor that was created. It was created in March. And then finally in 1954, the first nuclear-powered submarine, the USS Nautilus, was launched and is up and running. So lots of cool things happened between this time. But the real heyday of nuclear was actually between 1960 to 1975. So during the span of 15 or so years, this was like the real commercial energy boom. People like Westinghouse were creating nuclear reactors. I think their first one was called Yankee Row. It was a 250 megawatt electric nuclear power plant, which is like not insignificant for like a time like the 70s. So other different companies and other different countries were doing this as well. Basically, there was this huge boom in nuclear energy. So if you look at this little chart over here, this is nuclear reaction construction throughout the years. So if you look in this little chunk, you can see what a massive peak there was. This was like when everyone was building nuclear reactors. People thought it was super jazzy, and everyone was trying to jump on that. Unfortunately, all good things have to come to an end, though. From 1975 to 2002, which is about this chunk over here, you can see a massive decline, and then you can see that nothing really happens between the 90s and the 2000s, other than the fact that we were all born. But no new nuclear reactors were being commissioned during this time. And then today, we're kind of, I say we're back, but basically we're entering what people like to call a nuclear renaissance, which is between like this chunk over here. You can see that there's been a slight increase in nuclear reactors being produced, but basically there's been a whole new push for creating more advanced reactors. And currently, China, India, and South Korea, they are the main like players in this game. So China itself has 32 reactors operating at the moment, and they have 20 more commissioned, like literally right now, which is kind of insane. So yeah, do you guys have any questions about this? All right. So what causes like nuclear resurgence? this is the perfect time to talk about why nuclear power is cool. Again, you guys probably already know this. But the main reason is sustainability. So right now we've entered a phase in time where people are starting to realize that we've done damage to our environment. We've got to fix this. So global warming is a thing. I promise you it's actually a thing. And basically we're looking for a way to produce electricity without creating such a large carbon footprint. So if you look at this chart over here, you can see that this is where nuclear lies in the amount of carbon that it produces per, what's a unit, per gigawatt hour of electricity. When you look at that in comparison to coal and natural gas, which is our two primary sources of energy at the moment, you can see that this is definitely more attractive. So the statistic is actually that nuclear creates 75 times less carbon emission than coal does and 35 times less than natural gas does, which is incredible and amazing. So that's the main reason why we're going for nuclear. But there's other kinds of really good reasons. One is the amount of power output. You guys actually calculated this yourself in PSET 1. You know just how much power or energy comes out from one fission reaction. So just so you guys can double check if you got that statistic right in your PSET, it turns out that U-35 produces 3.5 million times more energy than burning 1 kilogram of coal does. So you can see that you definitely need a lot less fuel in a nuclear reactor than you do in a normal coal burning reactor. And then finally, the last thing would be energy security. So one of the good things about nuclear is that it can serve as a good baseload source of energy. So if you're working in the energy sector, you probably see this chart all the time of time versus energy that's being consumed. And it's kind of like this fluctuating little mass that stays fairly constant, but at certain times of the day, you need more energy than usual. So this is just kind of the energy demand during the day. That's what this chart kind of crudely depicts. So nuclear power is able to provide a good baseload source. That means it can provide constant energy at a really high level all the time. So this is why we kind of want to replace coal and natural gas with nuclear, because it can take this role. Other alternative forms of energy might be better for the environment, it might be safer and things like that, but it's not really able to do this. So for example, if you want to replace all the coal burning fire plants with solar panels, if it's not sunny that day, you're kind of out of luck, right? You can't produce energy if it's not sunny outside. Similar for wind. If it's not windy outside, you're not getting any electricity. Luckily for nuclear, it doesn't have to rely on any of these factors. You can continuously produce energy, right? So do you guys have any questions about what I've mentioned? Awesome. So now we'll talk a little bit about reactor types. I'll just tell you guys about some of the main ones and how they work. So how people like to divide up the reactor types is in generations. So generation 1, which is all the way over there, that refers to the trial reactors. These are the ones that didn't really produce all that electricity at all. They're more proof of concept kind of things. So that would be the Mark 1 that I mentioned to you guys earlier. Now we move on to generation 2. So generation 2 is actually what most of US reactors, the category that most US reactors fall into. So these were developed between the 70s and the 80s-ish, and these are the ones that are functioning mostly today. And then we have generation 3, 3+, and 4. So these are the new types of reactors that people are trying to build to create several improvements, but we'll talk about them a little bit more later. Okay? So I want to start off with light water reactors because, well, these are the reactors that are most common in the United States. So light water reactors, or LWRs, are mostly broken up into two subcategories, boiling water reactors and pressurized water reactors. So how you guys can think about reactors is that, honestly, they're just kind of glorified steam turbines. That's what they're doing. So let's start with boiling water reactors. So boiling water reactors, or BWRs, comprise about 21% of the reactors that are located and working in the United States. So it's a really, really simple mechanism, and we can walk through that right now. So over here, this little nubbin right over here, so this is the fuel core. So this is what the inside of a fuel core looks like, that picture over there. So the fuel core is basically just a bunch of rods of uranium. Sometimes it's clad in something like zirconium, and there's also control rods to help slow down the process. So uranium undergoes what? Fission. Yeah, so fission. So what gets released during a fission? And? Fission products. Cool, and? Neutrons, awesome. So those three things are all flying around inside the reactor core at the moment as the uranium undergoes fissions. So the isotopes, we just kind of let them be. I'm not completely sure what we do with them. We might filter them out, but I think they just kind of hang out there. The heat obviously goes to create power. We'll talk about that in just a second. But the neutrons come flying around. So those other neutrons can simulate other fissions. And the control rods are there to prevent, to make sure that there's not too many fissions happening in the control rod at a certain time. In the fuel core at a certain time. So anyway, going back to the heat. So the heat that gets created during these nuclear fissions, that goes and heats up the water. So this is just one loop of water, basically. So the water flows through the core, it heats it up, it creates steam. So the steam goes and spins a turbine, the turbine creates electricity, and it comes back and gets recondensed. That's literally it. That's all that happens during a BWR. Yeah, that's actually just it. So a cool thing about the BWR is because it's so simple, it's also incredibly, well not incredibly, but it is the cheapest option out there for creating nuclear power. One of the downsides is just that it might not be as energy efficient as it possibly could be, or not be able to create as much power as it possibly could if it was a cooler technology. But yeah, oh, and another downside is that because we have the nuclear material interacting with the water, and so this is a coolant pump, right? I mean, this is the coolant tube. So this is basically connected to a lake or an ocean or some other source of cold water, and that runs through the primary loop to cool down the water and recondense it into steam. If there ever is a breach between these two, the chances of leaking nuclear material into the environment exists. Like it's not high per se, but with BWRs there is a higher chance of leaking radioactive material into the environment. So that's one of the downsides of BWRs. Cool. Do you guys have any questions about this? Okay, awesome. So I just wanted to show you guys this picture again because here's the underside of a BWR. I make it sound like it's super simple and like a walk in the park, but this is actually the amount of technology that goes into one of these reactors. Like, look at all those wires. I don't even know what they all do, but it's kind of insane. So yeah. So the next kind of reactor that falls under the light water reactor category is the pressurized water reactors. So PWRs are actually more important, if you will, than BWRs. So remember, BWRs comprise about 21% of the reactors in the United States. PWRs comprise about 60% of the reactors in the United States. But they are functionally essentially the same, and it's just slightly more complicated. So over here we have our fuel core again, and again, all it's doing is heating up water with its fission reactions, but this time this water is pressurized. So does anyone know why you would want to pressurize the water? Yeah.
So it doesn't boil.
Yeah, exactly. So when you increase the pressure, you're also increasing the boiling point of the water, and that allows you to function at even higher temperatures than if you're working with a BWR, which gives you more energy efficiency. You guys will learn all about that in 2005, by the way. So yeah, so it heats up this pressurized water, and this pressurized water goes into a second loop, which again just heats up water that creates it into steam, that spins a turbine, that creates electricity, it gets recondensed, etc. And that's again all that there really is. So one of the upsides of using a PWR is, like I mentioned, the higher efficiency, but also the chance of leaking nuclear material into the environment becomes mitigated because you have two separate loops with the nuclear fuel being more isolated from the environment. If there is a breach between like the condenser loop and the secondary loop, not a big deal, like nothing really bad happens. You'd have to have breaches in both the loops, which is very unlikely to happen. Cool. Yeah. So do you guys have any questions about those two? Yeah.
What's the standard like operating temperature of these kinds of reactors?
I'm not completely sure, but if you Google it, you should be able to find it very easily. Okay. So this next picture is again just to show you that like I make it sound really simple and like a walk in the park, but it's really not. There's a lot going on. So this picture over here is basically just showing that there are a lot of redundancy systems inside these reactors. Like we don't just have one single primary loop, and if it fails, it fails. We actually have 4 at the same time, and this is just called the N-2 redundancy, something like that. Okay. So the next kind is something much cooler. It's called a heavy water reactor. Actually, it's just a little bit cooler. But the main heavy water reactor that everyone can kind of think of on their minds is CANDU, which is the one that's located in Canada. So the only difference between heavy water reactors and the light water reactors I mentioned before is that it uses heavy water instead of light water. Does anyone know what heavy water is?
Deuterium oxide.
Yeah, exactly. So it's just deuterium oxide. So remember, I'm sorry, this might seem inane, but this is water, right? And this is heavy water, where the D is just a hydrogen with two atomic particles instead. So 1 proton and 1 neutron. Right? Okay. So the reason why they decide to use heavy water instead of light water is because heavy water has a much lower absorption cross-section than light water does. So what this means is that when neutrons are flying around in the reactor, like there is a chance of it hitting a fission product and a piece of fissionable material and undergoing fission, but there's also a chance that the water that surrounds it will absorb that neutron. So if that neutron gets pulled out of the system, you're not able to create any more fissions. This is actually kind of a bad thing because the whole point of a nuclear reactor is to create heat and fission. So we don't want those neutrons to be absorbed. So you can see, if you look at those statistics, you can see that the absorption cross-section of H2, or deuterium, is like 0.0001 0.052 barns in comparison to H1, which is 0.332 barns. So I'm bad at math, but I think it's like 600 times less, right? Maybe, but anyway, so you can see why deuterium would be a good option for this. So because it's absorbing less, because it has a chance of absorbing less neutrons as it undergoes its processes, you're actually able to use a lower enriched uranium, which is really great because that lowers fuel cost. But the main downside of this is that even though you're lowering your fuel costs, deuterium is really expensive. It's about $1,000 or so per kilogram, which is kind of ridiculous because a kilogram of water is really not much at all, you know. So even though you're counteracting the lowered fuel costs with a higher water cost. Also, because you're using your reactor with lower enriched uranium, you actually have to change out your fuel more often. That fuel gets spent more quickly. I'll describe that in just a second. And therefore, you just have to keep replacing it more often than you would for a normal light water reactor. Cool. Questions about this one? Oh, I forgot to mention, but aside from that, everything else with the heavy water reactors and the PWRs, they're the same mechanisms. Okay. And then finally, we're going to move on to breeder reactors. So breeder reactors are a really cool idea, and they were most popular between like the 50s and the 60s-ish, in the very beginning of creating nuclear reactors. So what breeder reactors are, again, they're essentially the same thing as light water reactors I mentioned to you guys before, but instead now there's two little chunks of extra material. So do you guys know what the difference is between fissile, fertile, and fissionable material is? Cool. All right, so, let's start with fissile material. So fissile material is basically just the material that is willing to undergo a fission with a thermal neutron. So basically, when the thermal neutron gets absorbed by this fissionable material, it's willing to undergo a fission. Makes a lot of sense, right? So do you guys happen to remember what the energy of a thermal neutron is? You guys calculated this in PSET 1, huh?
1 MeV, or yeah, 1 MeV.
Lower than that. Yeah, 0.025 eV, like super low energy. And while we're at it, how do you calculate this? Boltzmann constant times T. Cool. Ooh, shoot. So main examples of fissile material would be U-235 and plutonium-239. There's 4 in total, but those are the 2 most important ones. Okay. So this is the main fuel that is inside a nuclear reactor, but it's not all just U-235. Like, you guys have heard of, oh shoot, what's it called? Enrichment, right? Like, enrichment is basically the amount of fissile material versus the amount of other fissionable material. So moving on to fissionable material. Okay. So fissionable material is just material that is able to undergo a fission after the absorption of a more energetic neutron. So that's all it is. So that's all it is. So an example of fissionable material that's inside the reactors at the same time is U-238. So if a U-238 absorbs a thermal neutron, it's probably not going to do much. But if it absorbs a neutron of about, like, I would say like 2 MeV, then it's more willing to undergo a fission. Cool. And then finally, we have fertile material. So fertile material is the basis for breeder reactors. But fertile material is just material that absorbs a neutron and then is able to become a piece of fissile material. So for our purposes, the main types of fertile material we use are U-238 and thorium-232. So if you look at these processes, you can see that U-238 absorbs a neutron, becomes U-239, undergoes a beta decay to become neptunium, and undergoes one more beta decay to become the beautiful plutonium-239. If we start with thorium-232 instead, absorbs a neutron, becomes thorium-233, undergoes a beta decay to become protactinium, becomes uranium-233, which is another fissile material, by the way, through a series of beta decays. Cool. So that's what breeder reactors are doing. They're adding extra chunks of uranium-238 and extra chunks of thorium-232 into the reactor. So if one of the neutrons, so imagine, okay, so if you're looking at the little fuel core, there's a bunch of neutrons that are flying around and heat and other isotopes and things like that. So some of the neutrons will go and create other fissions with the material that's hanging out in the red, but other neutrons might escape, and when they escape, instead of going into the water and dissipating and never to be seen again or being reflected, they instead create more fissile material. So you can understand why this is a kind of an attractive idea, is that you're creating your own fuel. You're able to work at a higher fuel efficiency because you don't need to add in as much fissile materials as you would for a normal light water reactor. So people were really fascinated with this idea, like I said, in the 50s and 60s, because back in the day, they legitimately thought that we would run out of U-235. But luckily, in the 60s, we discovered that we have a lot more uranium ore than we thought we did. We're probably not going to run out anytime soon. And after that discovery, people were not nearly as interested in breeder reactors. The reason being is that, one, because there's just this extra material that's hanging out, this extra material could be more fissile material that creates more reactions. It's not nearly as energy efficient, and power efficient. And it's also slightly more expensive because you're not being able to be power efficient. And it also is better on paper than it ever is in reality. So on paper, you're like, oh, this is great because I can just create more fissile materials. I never need to add more. This is never really truly sustainable. They always have to keep adding more fissile materials because it's not as perfect as they want it to be. So yeah. Any questions about these things? All right, cool beans. And then finally, we're going to move on to Generation 4 reactors. So Generation 4 reactors are all the new kind of reactors that people want to build. So the primary objective for these new designs of reactors, like the ones I just told you guys about, they're all good and well, but we want to make them better, right? We want to make them cleaner and safer and more cost effective, keep them robust yet sustainable, and also make them more resistant to people being able to divert materials into creating nuclear weapons. So yeah, so here are the 6 kinds of Generation 4 reactor types that were deemed to be the most promising. So there's gas-cooled fast reactors, lead-cooled fast reactors, molten salt reactors, xenon-cooled fast reactors, very high temperature gas reactors, and supercritical water-cooled reactors. So I'm going to be honest with you guys. I don't know all that much about these, and I don't want to like spew out information that might potentially be false. So if you guys are interested, one, you can talk to other lab members, people in this department. I know they're mostly Mike's group, actually. A lot of people in Mike's group are working on molten salt reactors, so you guys can like go ahead and ask them about that. Or if you're interested, you can read more about them with this hyperlink that I included over here. Hopefully he will post the slides online, and you guys can just click it, and there's an awesome source all about these different kinds of reactors. Okay. All right, any questions? Hi.
Where do these actually exist, or is it all just like
I'm pretty sure that they're just kind of proof of concept stage right now. Like there aren't any that are producing electricity in the United States, at least. Mm-hmm. Cool. Good question. All right. So all the things that we mentioned before, that like how great nuclear is and all the cool applications of it and how simple and easy reactors are, why aren't we using more of it? So currently in the US, there's only 99 operating reactors that are producing electricity, which makes up about 19% or about 20% of the total electricity output in the United States. The main players are still, you would imagine, coal and natural gas. So this is actually even worse in the rest of the world. In the rest of the world, there's only about 440 reactors spread around 30 countries. It produces only 14% of the global electricity. So these proportions are pretty low, and you're wondering, like, why aren't we using more nuclear power? What exactly is holding us back? So it turns out that the main things that are holding us back is just social, economic, and therefore like government hesitance to start using nuclear power more often. So the main reason why we're a little bit hesitant to start using more nuclear power is because of safety issues. So nuclear, none of us can argue that nuclear is like 100% safe. It actually does have some dangers associated with it, which is why it's so important that we're doing what we're doing. But if you guys look at this chart that I showed you guys in like the first or second slide, you'll notice that there are these events listed above. What are these words? 3 Mile Island, Chernobyl, Fukushima, what are they? Yeah, so there's some of our biggest nuclear accidents that we've experienced through history. And you can see that after a nuclear accident, you can see a pretty steep decline in the amount of nuclear reactors that are being commissioned. So this is especially noticeable at 3 Mile Island, which is essentially the first nuclear reactor accident that we all had to go through. You can see that after 3 Mile Island, you can see this massive decline in the amount of nuclear reactors being commissioned. This is probably causational. We can pretty much assume that. And then you can see that in Chernobyl, once Chernobyl happened, you can see like this also another massive decline. And again, at Fukushima, once again, like the amount of reactors being commissioned after the accident just declines dramatically. So I'm assuming you guys probably don't know exactly what happened during each of these accidents. Like you probably know that they exist, but like what happened during them. So if you do know, sorry, but if you don't know, you're about to know. So 3 Mile Island, which is the first one, it happened in 1979 on March 28th. So 3 Mile Island's reactor is a PWR located in Pennsylvania. So during this time, it underwent a core meltdown. So the cause of this is just the fact that there was some kind of mechanical or electrical system that prevented coolant water from being pumped into the primary system. So because there wasn't enough water coming to cool out the core began to overheat. So as the temperature of the core rises, the pressure also rises. So they notice this and they're like, oh shoot, we gotta fix that. So luckily there is like a little emergency valve that you can see in this little animation gets opened up and pressure gets released. So that's all good and well. But unfortunately, after the pressure is released, you should close the valve again and continue operation. But it became stuck. So this valve became stuck and they didn't realize that it became stuck because their equipment and their instrumentation wasn't able to detect that. So they continued operating again, but this valve was open. So there's actually water that was getting leaked out of this primary loop. So because the water was getting leaked, they noticed that, oh shoot, the pressure is dropping. Well, what do you do when the pressure is dropping? Apparently you have to make sure that there's not too many vibrations that could damage the reactor, so they shut off the coolant pumps. So, well, they lower the operation of the coolant pumps. So now there's water leaking out, so the core is getting hotter, but then they also took out the water that is usually used to cool the reactor core. So again, it's also getting hotter. So this combination of events led to a core meltdown. So the core melted down. That's never a good thing, by the way. So the core melted down. The reactor wasn't able to operate anymore. But luckily, at 3 Mile Island, there was containment that prevented radioactive isotopes from leaving the system. So they actually took a brief survey. Well, not a brief survey. It was probably a long experience. But I realized that the 2 million people who were around 2 Mile Island at the time, within like a 2-mile radius or like maybe like a 30-mile radius or something more like that, they realized that they didn't get much dose at all. They collected about a total of 1 millirem more dose than usual. So to put that in perspective, an X-ray is 6 millirem. So really nothing that bad happened at 3 Mile Island other than they had to shut it down and they had to do expensive repairs. But people weren't hurt, the environment wasn't damaged, it wasn't that bad of a situation. I think the effect was bigger in concept than it was in actual damage. Questions about 3 Mile Island accident? Alrighty. The next reactor accident, the big kahuna, I like to call it, is Chernobyl. So on April 25th, 1986, an RBMK reactor that was located in Ukraine exploded. So what they were doing at Chernobyl during the time of this explosion is that they were actually running, ironically enough, safety tests. They were running the reactor at low power to see how it behaves. So at low power, I don't think they quite realized this, but the coolant pumps in the reactor were also powered by the nuclear reactor being generated. So if they were running this at low power, their coolant pumps weren't getting enough energy to properly cool the fuel core. So that was unfortunate, and they realized that this is a bad thing. So the reactor started to go supercritical. So when they realized that the reactor was creating a lot more fissions than it should have been creating, they decided to insert the control rods. So thank goodness we have these high absorption control rods to slow things down, right? For some reason, not completely sure why they did this, but RBMKs, they have graphite tipped control rods. So as they lower the control rods into the water, this graphite tip, which doesn't effectively absorb neutrons, it displaced a little bit too much water than was necessary, and that caused the first explosion. So it went super duper critical and caused the first explosion at Chernobyl. Oh, by the way. Then for some reason, like a couple minutes later, there's a second explosion. They're not completely sure why the second explosion happened. To this day, we can't really pinpoint why. It could have been like building up helium or just a ton of other fission reactions. But there's a second explosion that actually just blew this entire core apart. So that kind of stunk, but it did stop the whole reaction. Because the supercritical mass was all blown apart, it was no longer supercritical. It was fine. The whole debacle stopped. But unfortunately, there was a lot of radioactive isotopes being spread into the environment. First of all, Chernobyl didn't have the same kind of containment that 3 Mile Island had, so these isotopes are just able to go everywhere. And also the second explosion had a lot of steam with it that carried these isotopes even further than they probably should have gone. So if you're looking at the sad statistics of Chernobyl, it turned out that 28 highly exposed reactor staff and emergency workers died from this radiation or from thermal burns during this time. And officials also believe that there's about 7,000 cases of thyroid cancer that occurred because of Chernobyl. They're pretty sure it was Chernobyl because these are all cases that happened in people who are less than 18 years old. So you guys know that no one really lives near Chernobyl at the moment. It's kind of been deemed unlivable because these radioactive isotopes literally went everywhere in this environment. Like it was in the water, it was in the plants. It's not safe to live there. It's a pretty radioactive environment. Luckily, we see that there are animals coming back now. If you look on nationalgeographic.com, there's like little deer roaming around Chernobyl. But it's been about like, how long has it been? Like 30, 40 years? People aren't advised to live here still. So Chernobyl was terrible. Questions? Yeah.
What does it mean for a reactor to go supercritical?
Oh yeah, sorry. So you guys will learn all about criticality in a little bit, but basically when I say supercritical, it just means that there's way too many fission reactions happening. Okay. Yeah?
You said it went supercritical because it wasn't being cooled enough? Or?
I think I might have skipped a detail. It wasn't being cooled enough so the water was evaporating, and then it became supercritical because there are not enough neutrons were being slowed down or absorbed. My bad, I'm sorry. Good? All right. So the next reactor accident that we were all alive for, which is cool, was Fukushima Daiichi. So Fukushima Daiichi happened in 2011 on March 11th, and Fukushima is in Japan. So these reactors, I think these are pressurized water reactors. Yeah, I think so. So following a major earthquake, the generators that, So following a major earthquake, the things that were cooling the core, they broke. I think they're just like power generators on the side that did, they broke the coolant pump. So there wasn't enough water being able to go to the fuel core. So this is a very similar problem. As you can see that in all these instances of the reactor incidents, it's just kind of like the fuel core was misbehaving and we weren't able to get enough coolant water to it. So following the earthquake, these coolant pumps broke. They're like, oh, that's okay. What we can do is we have backup generators to continue running the pumps. It'll be all okay. Nothing will happen. We're all good. And then a tsunami hit. So it was a 15-foot tsunami, I think. I think that 15-meter tsunami. Oh, good gosh. So a 15-meter tsunami hit, and it broke the generators. And then at that point, they're like, oh, no. So they had no other redundancy factors to continue pumping cool water into the fuel core. So again, there wasn't enough water in the core. It became supercritical. It began to melt. So the fuel rods began to melt, but this is actually another additional bad thing. So the water was evaporating, creating steam. There's zirconium. The fuel rods were coated with zirconium. So what you guys might not know is that when zirconium and steam interact with each other, that's not a good thing. It starts to explode. So as you can see, the reactors at Fukushima Daiichi began to explode. There was radioactive isotopes being spread out all around the country. You guys probably saw the lovely flow charts of like the radioactivity flowing out from Japan and making it to California and contaminating your fish and stuff like that. But luckily, no one was directly hurt by burns or radioactive exposure. Cool. All right, questions about Fukushima? Solid. So aside from these safety issues that happen, they get elevated in the news quite a lot. So these are mainly the things that people who don't really have any background in nuclear energy hear about nuclear energy. They're like, oh shoot, well, this thing is going to explode every 20 years. Like, why do we keep using this? Reactor accidents are actually pretty rare. Like, if you think about it, it's been about 60 or 70 years. We have 440 reactors happening around the country. there's 3 main accidents have happened. But because these are the things that people get ingrained into their mind, thank you, news stations, people think that nuclear reactors are incredibly dangerous, and that's why we have this social hesitance, which is why we aren't able to get enough government funding, and which is why there's all these bureaucracy loopholes to jump through, which is why nuclear power isn't more of a thing. Makes sense? Yeah. Another issue that's associated with nuclear power is nuclear waste. So what in the world do we do with it? So first of all, the main thing in nuclear waste is spent fuel. So like I mentioned to you guys, the spent fuel rods are made out of uranium oxide, but after undergoing a bunch of fissions, these uranium particles get transformed into other isotopes that aren't fissionable or fertile or even remotely fissile, right? So we eventually have to replace them and add in new rods, and this is a process that happens every like 12 or so years. I'm not completely sure on that statistic, but the main issue is like, what do we do with all this material? So this material that comes out is pretty radioactive. It's also incredibly hot, so it can be dangerous if someone decides to like come and eat it. So that's why we got to figure out a way to dispose it. So the primary way of disposing of this spent fuel is putting it into spent fuel pools. So spent fuel pools are just giant tanks of water that exist at the reactor. So these tanks of water are mixed with I believe it's boron, which is the neutron absorber. But basically just put the spent fuel rods all the way at the bottom of the pool. So this pool is about like 20 meters high, I think. And this is actually a really good solution because the water in the pool, it cools down the reactor rods. And also prevents a lot of neutrons from escaping because water is a really great neutron moderator. You guys all know this. And it turns out it's actually fairly safe. Apparently you can go swimming on the top of the reactor spent fuel pool and you'll be okay. Not be exposed to too much radiation if you want. So yeah. So this is the main solution that people have been using for years, but they realized that this isn't super sustainable because the amount of space that we have in these spent fuel pools is not infinite. Like we have way too much spent fuel to be able to just continue to store it in these spent fuel pools. So like, shoot, gotta find another solution. So the next solution was something called dry cask storage. So dry cask storage is just a way to keep this spent fuel surrounded by an inert gas. And it's held inside a cask just being probably like a steel drum that's like bolted and welded shut, and then there's additional pieces of shielding around it like cement and lead, etc. So there's just like gigantic tanks basically that are sitting outside. So they just put them outside the reactor. As you can see, it looks like it's sitting in a parking lot outside the reactor. And so this is an okay solution. So basically, what they do is they take the spent fuel, let it sit in the pool for about a year or so, maybe 2 or 3 years, and then they're able to take it out because at that point it's significantly less radioactive because you guys know how to calculate this too. You guys know like the half-life of different radioisotopes. You see that the radioactivity declines at a certain point. It's also more cool now, so they can put them in these tanks. So they let these tanks hang out outside. And this is an okay solution except for the fact that, again, we just have way too much spent fuel to be able to do this. It turns out that if you were to just keep all the spent fuel that we create in fuel casks, it would take up about 300 acres of land, which is absolutely inane, and obviously no one wants to take up that. Brief little side note, when I was Googling like images of dry cask storage, I was looking for the different types. What I found particularly disturbing was that there's only 2 types listed, vertical storage and horizontal storage. Like there's no other solutions other than these are giant tanks. But anyway, so people realized that we need to figure out yet another way to dispose of the spent fuel, hopefully a way that doesn't get in the way of people's backyards. So their idea was something called deep geological repositories. So deep geological repositories literally just means that they want to bury the nuclear waste very deep into the ground and never be able to retrieve it again. So the main push for this was, well, first of all, it's a permanent method of disposal. They hope to put it in the ground, never have to think about it again. So therefore, the regions that they choose to bury it in the ground have to fulfill a lot of criterion. So this criterion includes not having a lot of seismic activity because we are keeping this nuclear waste underground in these casks for like thousands of years. If there's a huge earthquake, those casks break, radiation gets everywhere. That's obviously not a good thing, so we gotta make sure that doesn't happen. We also have to make sure that there's not a lot of water that leaks through because the water can carry the radioisotopes and carry them into the environment, which is something else that we don't want to do. A lot of guys chuckled when you saw Yucca Mountain. So Yucca Mountain is like the primary push by the United States to find a deep geological repository somewhere in the United States so we can deal with our spent fuel. So in 2002, the main push for this began. They spent a lot of money. They spent like billions of dollars finding the perfect location to put our spent fuel. They had like 9 different locations, and they finally narrowed it down to Yucca Mountain. They're like, yes, this is the one. And they started like digging down deep into Yucca Mountain and making this happen. But then things weren't as peachy keen as they hoped it would be. So Yucca Mountain is located in Nevada. people of Nevada weren't happy about this. They're like, why are we getting tossed on nuclear waste? We don't even have nuclear reactors in Nevada. This is not fair. There's a lot of opposition. And because of this social opposition, there was government opposition and many loopholes we had to jump through. And so it's just becoming a huge disaster. They also realized that it wasn't as geologically sound as they had hoped. There was a lot more groundwater running through and seeping through Yucca Mountain than they thought there would be. So it's actually not as safe as they had hoped. So there's a huge debacle. Basically, the costs were rising, nothing much was happening. There's a bunch of different things preventing progression from happening. And then 2011, under the Obama administration, he just called it quits. There's no more government funding to Yucca Mountain. It's been abandoned. As you can see from this lovely Google picture, it's permanently closed. And you can also see that like 14 people went out of their way to review Yucca Mountain. But we're actually doing okay. It's at 3.6 stars, just like a normal like motel or something like that. But yeah. So that has been abandoned. This idea has currently been abandoned in the United States. We're kind of still looking for other solutions, but we really don't have it figured out all that well. There is one other kind of way of dealing with nuclear waste, which is repurposing. I personally think nuclear repurposing is the coolest option out there. And basically repurposing just means you take the spent fuel and you chemically separate out any material that could be continued to be used, any fissile material that could be continued to be used in other reactors. So basically you take the spent fuel, and it turns out that 96% of a used fuel assembly is recyclable. So you take the spent fuel, you take out what is useful, you throw away what's not useful, which is also still radioactive waste that has to be put in a fuel pool or something like that. But you have this precious fuel that you can like put into another reactor. So this is actually something that France and other places in Europe and Russia and Japan, they use repurposing quite a lot. For some reason, the United States doesn't do it. So the reason being is that this is a really cool idea. It's like recycling. It's like it's very clever. I think it's personally one of the cleverest solutions, but the issue is that it's kind of a really expensive process. So repurposing fuel takes a lot of money, and it turns out that the act of repurposing fuel actually costs more than just buying a new chunk of uranium-235, which is why we don't do it. It's not economically sound. So yeah. Do you guys have any questions about anything I've mentioned about deposition of nuclear waste? We're almost done. So all of these are issues, like we have a lot of nuclear waste to deal with. It is there is an inherent danger with using nuclear power, but the real thing that holds us back from just having nuclear power everywhere and creating about like 90% of our electricity, as we would hope it would, is economics. So in this world, money really matters a lot. So the economics of nuclear power is actually a really complicated topic, and it changes depending on who you talk to. There's a lot of factors that are involved, so you can include certain factors into your calculations, like, oh, the cost of building the reactor in the first place, or like the fuel cost, or operating cost, or maintenance cost, or like the amount of money that comes out of damaging the environment. You can weigh all these different factors in, and everyone turns out a different number. But basically, everyone you talk to, if you look at this chart, yellow is nuclear power, the gray is coal, and the blue is the natural gas. But basically, anyone you talk to, you can see that nuclear is not nearly as economic of a source of electricity generation as any other of these ones that I mentioned. Unless you talk to UK. UK thinks it's okay. But everyone else is saying that it's not as money efficient. So where are all these costs coming from? So the primary cost actually lies with something called capital costs. So capital cost is basically the sunk cost of just building the reactor. Building reactors takes billions of dollars. It also takes tons of time, and because it takes a lot of time, interest rates also jack up that price even further. So basically, it's just this massive investment they have to throw in immediately. And this is where most of the issues lie. Like, it's really hard to go to an investor and be like, hey, can I have $1 billion to build this nuclear reactor? It's going to take 5 years, and it's going to take 20 more years for you to get your profit back. How does that sound? No investor is going to be like, yeah, that's a good idea. So that's the main reason why we can't get nuclear up and running. We have a lot of plants, and we have the possibility to create a lot of plants, but we just don't have the money to do so because it's a huge chunk of money. Like I mentioned before, it takes a while to get your profit back. And also, if for some reason something happens and you have to stop building your reactor, well, you just lost $1 billion. Like, there's no turning back, right? If you look at this chart over here, which is breaking up the cost of nuclear energy per kilowatt hour, I believe, gigawatt hour? Kilowatt hour. You can see nuclear, coal, and natural gas. So this giant white chunk over here refers to the fuel. So if you can look at nuclear power, the majority of the cost actually doesn't come from nuclear fuel at all. It's just about 1 cent per kilowatt hour, as compared to natural gas, which the majority of the cost of the electricity actually comes from the fuel. If you look at operation and maintenance, again, it's not that large of a chunk. It's about the same as maintaining a coal power plant. But then if you look at the capital cost, which is the dark gray color, you can see how massive that is in comparison to building natural gas and coal firing plants. Right? Okay. So yeah, I think that's the main thing. So because it is more expensive. We can't compete with other forms of electricity. People buy the electricity that's cheapest, not necessarily the electricity that's best for our grandchildren or something like that. So yeah, so that's why nuclear power isn't more of a thing, and that ends my pretty lengthy slideshow. So do you guys have any questions about anything I mentioned? If you guys are interested about any of these topics, like if any of these things piqued your interest, I recommend going to nrc.gov. They have a lot of really cool information. Let me write that down because I talk quickly. That's basically where I got the majority of my information for this slideshow, and it is a reliable source. It might just be skewed a little bit pro-nuclear, so just keep that in mind. But there's a lot of crazy sources out there on the website, out there on the interwebs. Take them with a grain of salt. Take nrc.gov with less grains of salt than usual. Or if one of these things really piqued your interest, you guys can take 2204, which is a really cool class that's offered here, I think this spring, and if not this spring, next spring. But basically, it's called Nuclear Power Society. It's taught by a guy named Scott Kemp. He talks about all these things in a lot of detail and slower. So yeah, cool. So thank you guys so much for coming. I know you guys could have slept an extra hour, but instead you heard me ramble for an hour.